Hello, this is a section of work, a topic called Spectra. It's the second to last topic that we'll be doing in the whole of the higher course. We did refraction. The last one we did refraction. This one is spectra, and then we've got one more, which is interference after this. And then that's it. It's all done. So I think spectra should probably take about a week. May not take quite as long as that. We'll have to see how we go. Right, so let's start. What are spectra? Well, spectra, the word spectra is just the plural of spectrum, and we've seen different types of spectrum already. We have looked at the electromagnetic spectrum from third year, and the electromagnetic spectrum is just a complete range of radiation, right from very, very long waves, radio, right up to incredibly short waves with gamma. And right in the middle, there's the Roig-Abiv, the visible light spectrum. So we can think of a spectrum as being a range of radiations. Now, this particular unit is going to look at Roig-Abiv, the visible light spectrum, and where we get visible light spectra from. We've already seen that in the last unit. Refraction, take some sunlight, shine it through a prism. You get that splitting up effect caused by something called refraction, and you can see the visible light spectrum. You can't otherwise see the spectrum of light. You can't see what white light from the sun's made of until you actually split it up. So what sort of things produce these things called spectra? Well, glowing gases do, and again we did a little bit about this at National 5 in the space unit. We've got over 100 elements in the periodic table, forgetting all the very short-lived ones at the top end, all the high-numbered ones, radioactive ones. It's possible actually to turn every single element into a gas. All you've got to do is heat up the element. If it's a solid, like carbon, for instance, you can heat up carbon, it will turn into a gas, and then you can trap the gas and you can put it in some sort of tube. What sort of tube? Well, not a tube like a test tube as such, but you can put it in a glass tube and you can seal it up. And we've got some of those. You've probably got some in your house and you don't realize it. Fluorescent tubes. And you'll have a fluorescent tube is a long glass tube, and it's got a couple of little metal electrical connectors sticking out the end. You might have them in rooms in the house. So we've certainly got them in the physics labs. All the lighting in the physics labs is produced by these things called fluorescent tubes. And the tube is a sealed tube, and it's got a gas in it, a low pressure gas. And when you pass electricity through the gas, when you turn on the light switch, then you get light. Light's emitted. Now, you can do this with any element you like. I said, you can take carbon, heat it up, turn it into a gas, trap the gas in a tube, and pass electricity through it, and you get some light emitted. So these gases glow when they get, here's a word for you, when they get excited. And that's a physics word. It's not like, oh, I'm getting excited because it's summer holidays, but these gases get excited. And it's all to do with what the electrons do in the gas. We've already covered a little bit about this, about electrons living in things called energy levels. We did this in electricity, and you get electrons jumping up and down. They take in energy, they jump up into an energy level, and then when they fall down, they emit some light. So this is sort of bringing some of that stuff together about electrons in gases, and that's what happens. Now, this gas sitting in the tube, it's not excited. The tube's off. There's no electricity flowing through it. Electricity is a type of energy, but you turn on the electricity, and the electrical energy makes the electrons leap up into a higher energy level, and then when they've had enough of being up there in that higher energy level, they fall back down and they give out light. So we've already met some of these ideas, but we're going to go into that in a little bit more detail now, and especially with this idea of gases and how they produce light in a little bit more detail. But before I get on to doing some actual physics, I want to introduce you to an analogy. You know that I quite like analogies. Earlier on in the photoelectric effect, we had an analogy to do with something called a coconut shy, and what happens when you throw a ball at a coconut. How does that explain how the photoelectric effect works? Well, I want to start with an analogy, and then I'll introduce the physics afterwards. And here's a little story. You know, I quite like my stories. If we go back in time to the end of the Second War, the end of the Second War, certainly in Japan, ended very, very dramatically when the Americans dropped a couple of nuclear weapons on Japan. Only the Americans had the nuclear weapons at that time. The Germans were trying to develop them, but they failed before they could actually get them produced. And the war in Europe was over a little bit before the war in the Far East and in Japan. But following the war ended in 1945. Following the war for about the next 20, 30 years, most of the big, what are called superpowers, developed their own nuclear weapons. So Britain's got some, and it's no big secret where they are. They're all on board submarines, which are either out at sea, or when they come back at sea, they're parked up in a submarine yard, a boat yard on the west coast of Scotland. And I gather at the moment that the UK owns about 60 of these nuclear weapons, and they're ready to get fired at anybody who upsets the Prime Minister at the time. Other big countries have got them, Russians, the Americans. Most of the big, what are called superpowers, have these nuclear weapons. So if you're going to have a nuclear weapon attack coming in, you'd better be protected. I think all of us living above ground in our houses, we're going to get wiped out if a nuclear weapon comes over and blows up. So the government of the day decided that they would build some what are called nuclear bunkers. And for many years, these nuclear bunkers, and a bunker is an underground space to live in. For many, many years, these bunkers were quite secret, and it wasn't generally known where they are. And there's certainly one down in Fife. It's called the Secret Bunker, and they're not used anymore. And the Secret Bunker is all over road signs, and you can actually take a trip in Fife down into this underground nuclear bunker. There is one in Inverness. I've been lucky enough to go down into it. It's a fascinating thing. It's up near Regmore Hospital, and it's in the middle of a housing estate. And occasionally they open up the doors of the bunker, and you can go down, and it literally is down because it's built underground, and it goes down many, many levels underground. There are a whole series of other much smaller nuclear bunkers, and the nearest one to Fortrose is actually on the golf course right down the end near the lighthouse, and it's not obvious where it is because you can't see much of it. It's there's a few concrete bits sticking up above ground, and it's got a lid on it which is sealed up with a padlock. I've been down to have a look at it, and if you can get inside it, you go down a ladder and you go down underground, and all these bunkers are protected underground so that if somebody does drop a big nuclear weapon on us, we're all going to get wiped out because we're above ground. But if you happen to be lucky enough to live in one of these bunkers underground, then you might actually survive. And the big one in Inverness, the idea was that the council officials would all go into the bunker, and they'd still be able to run the country. Who they'd be running the country for, I don't know, because we'd all be dead. But they'd be able to run the country from underground in the safety of their bunker. So what does the bunker look like? You've got ground level up here. And there's all you can really see on the surface is a sort of doorway, and you can go in the doorway and immediately you go down some stairs or down in a lift, and you can go down a level to the sort of first level, and you can go down and down and down. And as you go further down, these levels can get quite big. So this is a sort of an analogy as to where we're going with glowing gases and electrons, and you have to bear with me at the moment. But you go down and you go underground, and there's meeting rooms on one level, and then there's bedrooms, and then there's kitchens, and then you've got down the bottom, you might have all the plant material. You might, I don't mean plants like growing green plants, things like generators and water supply and purification systems. Now the top levels, they're not very far apart. They're just to get away underground, and it's probably not much higher than a sort of a normal living room. But as you go down, you get these bigger meeting rooms, and certainly at the bottom, to accommodate all the big machinery with all the pipes and stuff and hot water going everywhere. These levels are quite big. But you can imagine that you might have a lift system, and you can get into the lift system, and ground level, that would be like ground zero. Ground zero is the ground level, and then you go down to level -1 down in the lift, -2, -3, -4, -5. So you go down in the lift, and instead of like most of the lifts you see that are in blocks of flats, or I think the biggest lift in Inverness is probably in Regmore Hospital, where there's 7 floors, and you already start at ground level and you go up +1, +2, +3. If you're underground in one of these bunkers, and so the levels will be numbered with negative numbers. And I want to use this idea of different levels to introduce the idea of spectra and how spectra are formed in things like glowing gases, with the idea that we've got levels, that you start on a level 0 and then you drop down levels. So you can think of it as a lift system going down, where the floors actually get wider and wider to accommodate more and more equipment as you go deeper down. This one only goes down to -5. Right, okay, so that's my idea of a nuclear bunker. You could have other ideas of levels, and the important thing is we've got levels. That's one important concept I want to introduce, and we're going to start on our ground level, which is level 0, and we're going to go down a whole series of different levels. And this is important, that we can drop down levels. And this is exactly what electrons can do. They can live in what are called different levels. And electrons, where are these electrons? Well, they're orbiting around a nucleus, and the nucleus is a way down here. It's a long, long way down. And the electrons don't get actually that close to the nucleus, and they tend to stay at quite some distance, and they're quite happily living in these different levels, not just statically, but they're also going round and round and round the nucleus. And we'll come on to this idea in a minute. Okay, so I'm not really expecting you to write anything just at the minute, but this is an analogy, as I've said, different levels. We're going to look at how much energy you might have in these different levels, and we would start with saying at ground level here, this would be energy level 0, and as you go down, you'd have -1 unit of energy, -2 units of energy, -3 as you go lower and lower down. So we can think of these things as levels, and we can put things in these different levels. You could have anything you like. You could have people living in a level. You can have storerooms full of food in a different level. So anything that you can stack up like that is an analogy to where we're going with where electrons are. And at the top, you've got actually here, this is the highest you can go. As a person, that's as high as you can go. You can get out to this level. But if you want to be safe, you're going to have to live down underground in your bunker. Okay. Right, so that's an analogy. Let's move on. Now, if we have a look at the picture of an atom, now atoms are very, very complicated things. We don't have a great idea of what they look like, so we need to build up some sort of model or idea of what an atom looks like. And possibly, you can start copying this down now. Possibly the simplest idea of an atom is we've got a nucleus made of protons and neutrons, and we've obviously done a lot of that sort of stuff in the nuclear reactions section. We didn't talk really at all about the electrons, and we've got the popular idea that electrons are sort of in an orbit, whizzing around like this. We'd have lots of electrons in different orbits or shells, if you like, if you want to use a word from chemistry. That's quite difficult to draw, so we could have a simpler idea, and the sort of simpler idea is that we just have the nucleus in the middle, and we're just going to stick our electrons in a circle in these different orbits. Okay, and electrons are living here, and they can do various things. They can whiz around, and they can change their levels if they need to. That is a complicated idea because you're going to have these lots and lots of electrons living in lots and lots of different shells, and even that's quite complicated. So what we're going to do is to make it really, really simple, and we're going to look at the simplest possible element we've got, and the simplest possible element is that of hydrogen. And hydrogen is nice and easy for us to work at. If you want to look at energy levels and where electrons live and shells and stuff for more complicated atoms, it is more complicated. So we're going to start off with a very, very simple idea that we've got a positive proton, and around it there is just one single electron, and it's behaving itself quite nicely, and it's whizzing round and round and here, and it's probably in 3 dimensions, and it's probably coming out this way and going around that way. But we're just going to draw our model like this, and this is the very simplest model of the hydrogen atom that we can get. So it's got one proton, which is obviously positive, and it's got one electron, and that's it, and the electron is whizzing round and round and round. And we're just going to stick with hydrogen. We're just going to stick with hydrogen for now because it's the easiest model to deal with. Okay, now if the hydrogen atom is behaving itself, the electron will just be going around and round here. But we've already seen in the photoelectric effect that we can shine light on our electron. And what we were doing with the photoelectric effect is we were shining light on electrons in zinc, because zinc's a nice material where you can get electrons to actually leave. So we're going to come back to this idea that we looked at in the photoelectric effect of incoming photons of energy. And the incoming photon of energy, if it hits an electron, one photon hitting one electron, it can give that electron some energy. Well, what does the electron do? The electron could absorb that energy, and then it's got enough energy to move up into a higher orbit. Or if you give it a whole load of energy, it can actually escape altogether. So it's possible for this electron, this single electron, to absorb the energy, and then it could, it's a bit like going up the rungs or the floors in the nuclear bunker. That single electron could then absorb the energy, and it can go up what's called an energy level. And then it would just be orbiting at a slightly further level away from the proton like that. And if another photon came in, it could promote it to another energy level. And we can get this idea that if you go back to the nuclear bunker, that the best place to be might be right down in the bottom of the bunker, right down the bottom. And if you've got enough energy, you could climb the stairs, because you'd need energy. You'd need to have breakfast as a person, and you could climb the stairs and you could get yourself up to another higher energy level. And if you get more energy, you can go up the next energy level, and eventually you'd come back up to ground level, which is ground level 0, having gone from, say, -3 level to -2 to -1. And if you actually get enough energy again, then you can obviously run off and you can go and do whatever you like. And we've seen that idea of gaining energy and escaping from an atom, electrons escaping energy. So if you think of people as electrons, then you can, as you get energy, you can go up. Okay, now the natural place for anything to exist is back down at the bottom, the very, very bottom subterranean level. And you can see this in nature, that places where they've put up buildings, and you've got ground level here, and you put up a building, and if you come back 1,000 years later, where is everything? It's all back down at ground level. The natural thing in nature is things want to go back to ground level. They fall over, buildings fall apart, bricks fall off, the roof gets blown off, and everything ends up back down. So although you can go up, you're going to need energy to go up. The natural place that you want to be in an atom, and the electron in an atom wants to be, is back down here, because eventually it will just fall back down. So I want you to think about this idea that to get an electron to go up a level, you're going to have to put energy in. And if you go back down, you'll get some energy out. If you take a ball, here's the ground. If you want to pick up a ball off the ground, you're going to have to give that ball some potential energy to lift it up. You're going to have to put energy in to lift the ball up. And once the ball's up here, it's not going to stay there forever. It's going to drop back down, and it's going to, on its way down, it's going to convert the energy that you put in. It's going to give back the energy. If it's a ball, it's going to give that back as kinetic energy on the way out. And this is a key idea. All these things, buildings wanting to fall down, picking up a ball and picking it up and dropping it back down, are all models or analogies for how electrons behave. So if I want to take this electron from its bottom, lowest most energy level, I'm going to have to put energy in to raise it up. And it could go up a number of different energy levels. And if you give it enough energy, the electron could fly off. We've seen that before. If you don't quite give it enough energy, then it will go up and it would stay here, and it eventually would fall back down. And as it falls back down, it's going to give energy out. So to get the electron up, put energy in. If the electron falls down, you get energy out. So I hope you've drawn some of this stuff here as I've been talking, and I'm just going to put that last sentence in. And this is just a single electron, and it can live in different levels. If you wish to raise an electron up to a higher energy level, you must put energy in to climb up the stairs. And the electron won't stay there forever. Just like the ball, if you pick the ball up, or the building that tumbles down, when the electron falls back down, it gives out energy. There you are. That's quite important. That's an important statement about what's going on. So let's go back to our diagram of the proton and the electron. and it can orbit in this level, or this level, or this level, or this level, and eventually it could get out and disappear off completely if you want. Now, it's going to take up too much room to keep drawing this whole idea. So what we're going to do is we're just going to concentrate on one little bit of this, what's called an energy level diagram. I'm not even going to look at the where the nucleus is, because the nucleus is so far away. This is completely not to scale. So we're going to draw this, and this is going to be just like in the nuclear bunker. This is going to be energy level -4, and I'll transfer the information over here. So I've got energy level -4. I'll call it E4, and it's got a minus number because you're going up and down from ground level. Ground level's up here, and then you've got quite a way away, you've got energy level -E3. That's over here, and then you've got number 2 energy level, and they get closer together as you go up. Energy level is 2, 4, 3, 2, 1, and then 0 is up here, which means you can escape. That's ground level. Energy level closer together minus energy level 1, and then here you've got energy level 0, and that's your ground level, and that's where you can escape from. Okay, so we're not going to draw the whole thing. We'll just draw these little bits, and obviously they come around here in big circles. So we're going to stick with this idea. I'll get rid of that one. We're going to stick with this idea, and we're going to look at these things called energy levels. So this is an energy level diagram. And how do we get our electron to go from here, energy level 4, to energy level 3? We have to put energy in. And what happens if that electron decides it's had enough and it wants to go back down to the bottom level? Then you'll get some energy out. Now, this whole idea of a single electron living in a number of levels was developed. I can't even spell energy. I should have a space there for level. I'm sure you can sort that out. This idea of energy levels and this diagram was invented way back in the early 1900s by a Danish physicist whose name was Niels Bohr. And he became famous. I think he even got a Nobel Prize for coming up with this idea. And this energy level diagram is called the Bohr model of the electron levels. It's called the Bohr model. Okay, and so you can think of it as having different levels. You can think of it as being shelves in a room. If you've got shelves in a room, and you can put things on shelves, and the electrons can be at different levels. And if you want to pick up a tin of food from the bottom shelf, you're going to have to put some energy in to lift it up. And if it tumbles off, it will give out some energy. Most shelves are at nice equal, possibly equal spacings, but the Bohr model, of energy levels actually has all the energy levels get closer and closer the nearer you get to the surface. So think of this shelves with tins of food on, the nuclear bunker, anything like that, and transfer that into where electrons live. And this is the model invented by Niels Bohr. So it's called the Bohr model of the atom. And we're just going to stick with hydrogen and its 1 electron because it's easiest to think about. It's not worrying, but if you want more electrons, it's much more complicated, and that is a bit of a worry. Okay, so let's move on a little bit. And how does this relate to these things called spectra? And we're going to come back to this. This is key to this whole subtopic. Okay, and there are a number of different types of light spectra that we need to look at. And the first one we could look at, I'm just going to do a very brief overview, is something called an absorption spectrum. Okay, so what happens in something called an absorption spectrum is that energy is absorbed. And if we go back to our model of the Bohr model, if I've got some incoming energy from a photon, an electron might be down here, and the electron will absorb the energy of the photon, and that will make the electron go up an energy level. So what is an absorption spectrum? It's some light that is it's a particular color of light bands or colors, which is caused by electrons gaining energy. They're absorbing it. That's what the word absorption means. They're gaining energy by absorbing the energy carried by a photon. So that's one type of spectrum that we're going to look at. It's called an absorption spectrum. Okay, now the second type of spectrum that we're going to look at is called an emission spectrum. And to emit means to give something off, to get rid of it. So what is an emission spectrum? Well, it's actually caused by, we'll go back to our model of our electrons. So let's say we've got an electron here. What happens is energy is given out when an electron goes back down a level. So I'll say that electrons release or emit energy, and as they do so, what's happening here is, in this first one, you're absorbing the energy, you're taking the energy in, so that energy then disappears and gets stored in the electron. What happens here is when the electron goes back out, the energy is given back out, and it's usually given back out as a photon of light, for instance. And so energy is emitted when the electron falls back down. So electrons release or emit energy when they fall back down. And these are two different phenomena that we're going to look at. Energy getting absorbed, which makes electrons go up, and energy released when electrons go back down. And it's all to do with the energy that a photon carries. An incoming photon of light gives its energy to electron, makes it go up, and when the electron jumps down, the photon of energy goes back out again. Okay, we already know what photons are, and photons is a bundle of energy that travels in what's called a discrete or self-contained bundle. Okay, and that's something we've done before. So going up, absorbing energy, going down, emitting energy. There you go. And we can again extend this into our complete orbit system if we wanted, but it's much tighter to draw these in these partial orbits or energy levels. Right then, so hydrogen, let's return to hydrogen because it is the simplest one. The more electrons you get, the more complicated these levels are. So we're just going to stick with hydrogen as our basic building block. And if you carried on with physics, after this. Certainly at university level, you could learn how the energy levels are built up for more complicated elements. So energy level diagram. Let's be precise. Energy level diagram for hydrogen. Okay, so we've got ground level up here. Here's our ground level. And that is energy level 0 that we've already discussed. And then we've got a level which is just a little bit below it. I'm going to stretch this out, and it's going to take up quite a lot of space. And I'm just going to change the numbering system a little bit. I'm going to have another level here. How many have I got? I've got a level that's right down here. Okay, this is how much energy an electron has when it's here. Okay, so I'm going to go down. I'm going to go down to this -1 level, and we can actually work out, physicists have worked out how much energy it takes to move up a level and how much energy is given out when you go down a level. And at the top, you haven't got any, but to get from here to here and back down again, this energy level is -2.4, and it's an incredibly small amount of energy, as you can imagine, times 10 to the -19 joules. And let's have this one here, and it is -5.4 times 10 to the -19 joules. And this one down here, it's quite a long way further down, and the energy at this level, this minus level going down, is -21.8 times 10 to the -19 joules. So these are the energy levels that we've got. Now I'm going to change my numbering system. This is the amount of energy that we have, but I'm going to change my numbering levels, and I'm going to make this E0, and I'm going to make this E1, and I'm going to make this E2. Okay, and as far as the electron is concerned, the electron is happiest living at this lowest level here. That's where it would happily be all day long. Okay, it's waiting to get some energy to go up, or it's giving out some energy to go down to the bottom. And this level is called, as far as the electron is concerned, because it's an underground dweller, it doesn't really know about us where we live up here above the nuclear bunker. This is called the ground state. The bottom level is called the ground state. Now this top level here, where you can actually, if you get enough energy, you can go all the way to the surface and then you can run off. Okay, in terms of electrons escaping, in physics and chemistry, the electrons escaping from an atom, that's called ionization level. That's called ionization. So this level where the electron can actually go from here and whiz off somewhere, as we saw in the photoelectric effect, this level is called the ionization level, right at the top here, furthest away from the nucleus, ready for the electron to escape. And anything in between is called an excited level. So this is one of the excited levels. This is called excited level 2. Excited levels, and there are more than one of them. So the very lowest one in any, that's supposed to be an E there as well, any atom, the lowest down that you can get down in your bunker, or the lowest level on a shelf in your pantry, is called the ground state, and we'll number them up from there. But remember, we're going to have to look at energy levels as you go lower and lower. We're going to say that this level, energy 0, anything lower is a minus number, just like going down in the lift, minus Imagine having a level called minus 2.4 and another level called minus 5.4 and another level called minus 21.8, and these levels get stretched out as you go down. Okay, so that's the names, and those are the numbers. Now you need to remember the names: ground state, excited, can't spell again, ground state, excited, and ionization level, and you need to know the names. You don't need to remember the numbers. The numbers would be given to you in any question that you'd have to do in a test or exam. Right. Now, these are levels and they're called discrete levels. What does discrete mean? Discrete means that the electron can only live at this level. It can't hover in the middle. It's either down here on this particular level or it's up here at this level. It can't live in the middle. Just like being in your bunker, you have to stand on the floor at each level. Another way of looking at this is to think of it as rungs on a ladder. You can go up a ladder and climb up the side of a house, but this is a rung. You can't put your foot and climb up from here. You are either here on a rung or you're here. You're either here in your nuclear bunker or you're here, or you're possibly here, or you're here. But you cannot exist in the spaces in between. So these levels, which are fixed, you can't live in here. You can't live in the space hovering above the floor. These are called discrete energy levels. And you can only live on a particular level. They can only exist there. Electrons can only exist on these discrete levels, discrete energy levels. I hope this is appearing just. I think it's just appearing. I can see it. They can only exist. Okay, right. Now, how could you get from the ground state with this, what's called energy level, this is its floor number, if you like, how could you get an electron to go from there to there? Because it can only go from there. In fact, I'm going to put this over here. I'm only going to get the electron. I can only get the electron to go from there up to there if it absorbs some amount of energy. Now, how much energy would you need to get an electron from there to there? Well, it's really easy to calculate this. What you do is you take 5.4 times 10 to the negative 19 away from 21.8 times 10 to the negative 19, and I'm just going to work that out on my calculator, 21.8. Now, because these are negative 19s, I can sort of dispense with them. I'm going to do 21.8, take away 5.4, and that is equal to 16.4. 16.4. What I would need to do is give this electron 16.4 times 10 to the negative 19 joules, and it will go from there to there. What happens if I give it 16.3 times 10 to the negative 19 joules? Then it can only get to here because it's not enough energy to make the next level. And so nothing can live in this level. So it's not interested. It's like the electron says, well, there's no point in giving me 16.3. I need 16.4. And then I can get to there, and that's the next level. If I've got only, I don't know, 5.0 times 10 to the negative 19 joules, I'm not even going to get a third of the way up. And so there's no point, because I cannot live in this space. I can only stop at different energy levels. What happens if I give it 16.5? Well, 16.5 is too much. Remember, you can't live in a space here. So if I take 16.5, the electron would think it could go to here but then pointing it going to there because it can't live there. It can only get off the lift when the lift is at the right level. It can't go in between level, and it can't go in an in-between level. So you need to give the electron 16.4 times 10 to the negative 19 joules of energy, and then it can go precisely from energy level 0 to energy level 1. And that's it. So how could it get that energy? Well, it can get that energy from a photon. And a photon can come in here. If the photon carries 16.3 units of energy, then this electron isn't interested, and the photon just disappears, and it goes through and comes out the other side of the atom somewhere, and the electron says, I'm not interested. Only if this photon of incoming energy carries exactly 16.4 times 10 to the negative 19 joules can the electron leap up there. No other energy is enough or too much. It's got to be exactly that. So you've got to find a photon that comes in here with 16.4 times 10 to the negative 19 joules, then it can make that jump. Okay. Now, once it's there, what could the electron do? Well, if it hangs around long enough, it might just fall back down again, in which case it would give out, it would emit. It's already absorbed some energy to get up. It can emit the energy, and if it falls back down, it will emit a photon of light with exactly that amount of energy as it falls back down. That shouldn't be too difficult to understand. Okay, right. Now, electrons, being clever, can sometimes miss out an energy level, and it might be possible to get all the way to this level here in one go. And it would say, I'm actually going to press the lift button, and I'm at my bottom level, my ground state, and I'm not interested in going to level 1. I press the button for number 2, and I'm going to go up, and I'm going to go up, and I'm going to go all the way up to there. How much energy would the electron need to get from there to there? Well, it's quite simple. You take your 21.8 and you subtract from it 2.4. And if I do that on my calculator, 21.8 minus 2.4, and that is equal to 19.4. So to get this move up here, 19.4 times 10 to the negative 19 joules. But the electron might have had some job to do on this level, so it could have gone to there, and then it could have hung around here for a bit, and before it got fed up and went back down again, it could go from there to there. So the electron's got a number of ways of getting up to this level. It could either take the lift and go and not even bother stopping here, or it could do that little bit there on its own. It could do this bit to start with, and then later on it could do that there. And how much energy would it need to go from there to there? Well, it's very simple. Take 5.4, take 2.4 away from it, and 5.4 take away 2.4 is exactly 3 times 10 to the negative 19 joules, and then it can make that little step there. So there are 3 ways in which the electron can get there. It can go there and stop is 1, and then another one, 2, or it can do that. So there's only one way it can go there, from this one to this one, only one route, and that's it. But to get to that next level, it can do it in 2 bits. It can go there first, and then it can go there, or it can take the big jump. What happens if it wants to go back down again? Well, supposing it's up here, how can it get back from energy level 2 back to 0? It can take the lift and it can go all the way down in one go, like that. Or it could go down there and stop off for a while and hang about. What happens when it gets there? It can go from there and it can go back down again. So in the same way that it can get up in a number of steps, it can go back down in a number of steps. And we can work out how much energy it takes to go up. To go from there to there, you need to have precisely 3 times 10 to the negative 19 joules to go from there to there. What happens if the electron wants to go back down? It's absorbed energy to go in. It's absorbed 3 units of energy. But when it goes back down, it will give out, it will emit 3 times 10 to the negative 19 joules of energy to go back down there, because that's the difference in energies from there to there. Then it could go back down, and how much energy would it give out? It would give out the difference between these two here. Or it could go in one go and it might not even bother stopping there, in which case you'd need to take 21.8, take away 2.4 from it, and then that's the amount of energy the electron would give out or emit when it goes all the way from level 2 down to level 0. I think this is reasonably straightforward. You can only go in these what are called discrete steps, and there are a number of ways of doing that. Okay, so this is quite simple for our hydrogen atom. Let's just get rid of these, because I'd like to finish off with how do we get to the top level. And I'm going to redraw this so it has a bit more of a logical sense to it. How am I going to get my electron from here all the way to this ionization level? Well, let's do this. I can go 1 and stop, and then I can go 2 and stop, and I can go 3, and then I'm ready to leave and go off. Okay, that's 3 ways of getting from there to there. Get in the lift, press 1 floor up, stop, press 1 floor up, stop, press 1 floor up and stop. Well, what's another way of getting up? I could go all the way there and then all the way there. Well, I'm not going to count that one again because I've already got it, but I can make that move and go from there, not bother stopping at this level and going there, and then I've got the last way, which I've already measured. What's another way of getting from there to there? Well, I can go all the way there in 1 step. Okay, so how many ways do I have of getting from here to here back to my ionization level? 1, 2, 3, 4, 5. There are 5 ways of getting from there up to there. And in the same way, there are 5 ways of descending. You could descend all the way in one go, or you could go the 1 level, stop, then a 2nd level and stop, then a 3rd level and stop. There are 5 ways of going up, and there are 5 ways of going down. So 5 routes up. Okay, 5 routes up. Good. I think you're getting there slowly. Now, we could have a slightly more complicated system where we can stick in another one. So we'll have our ground state. And instead of having 2 excited states, we'll have 3. So I'll put 1 in there and 1 a bit closer there and 1 a bit closer there. And then the top one would be there. And I'm going to call these, call them what I want really. Could call this the ground. That's the ionization level, obviously, and I've got 3 excited states in the middle. Or excited levels. Right, this is the level where you can whiz off, and this is your lowest level. How many ways have I got to go from there to there? Well, let's start off here. Let's do it in bits. I've got 1, then I've got 2, then I've got 3, and then I've got 4. I can stop off at every floor on the way up. What I will then do is I'll move over, and I've got that one. Okay, and then I can take that one, and I can take that one. But is there another way of getting to there that doesn't involve stopping there? And it is. It's that. And you can probably work out what's coming next. This is my first one. This is my second one. Here you go. I can go to there, and then I can transfer back to that one. And lastly, I can do the whole thing all in a one. And how many different steps are there? 1, 2, 3, 4, 5, 6, 7, 8. There's 8 ways of getting to the surface level, the ionization level, if I've got an excited state. And I could just carry on with this. I could add another one in and call it a fourth excited state. And I could put another one here, and this becomes another excited state, and this becomes a new ionization level. And how could I get there? Well, I'd go back and I'd start adding up 1, 2, 3, 4. And then I'd have another one here, which would be 5. And then I can do that one and that one. And then that I can do that one and that one. And then that one. Or I can do that there. One. Is that all? Are there any other ways of getting up there? You have to say to yourself, all in individual steps. Take 2. I don't want to take another one because I've already got that. I can take 2 together, which is okay. And another one that's the same as that. I can do 3. So I'm building up. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 ways of getting my electron up to the top there. Right. I think what I want to do is stop just there, because I think that's long enough for this first lesson, and you've got a good idea now. I think all of these, this is all called the Bohr model of the atom, and how an electron can escape. What happens to get an electron to escape? You need to put energy in. What happens if the electron doesn't escape? It can come back down. It can come back down in a number of different steps. So that's absorption of energy to get up. And what happens when it comes back down again? It emits energy on the way down. We've had a look at energy levels. We know how to work out how much energy to get from there to there. You just look at the numbers given to you, take one from the other, or from there to there, take the numbers away. So we've done all of that for now, and I'm going to stop there and I'll move on in the next lesson. I think that's long enough for this first one.